Okay, it's time to start quantifying the level of acidity or basicity with respect to these acids and bases that we've been discussing, in particular these weak acids and bases. And it starts with the autoionization of water. Recall that water is amphoteric or amphiprotic. What that means is that water can act as a Bronsted-Lowry acid and it can lose a proton and form hydroxide, or water can act as a Bronsted-Lowry base and it can accept a proton and form hydronium. So in pure water, you can think of a small amount of molecules acting as a Bronsted-Lowry base and a small amount of water molecules acting as a Bronsted-Lowry acid. And the acid is going to donate a proton to the base. The base will then form its conjugate acid, hydronium, and the Bronsted-Lowry acid, which donated its proton, will form the conjugate base hydroxide. So you can think about in pure water a very few number of molecules acting as a base and a few number of molecules acting as an acid, and they're going to form a small amount of hydronium and hydroxide in solution. And we will refer to this process as the autoionization of water. And in any aqueous solution, this process takes place. What this gives us is an equilibrium process, right? Where water is a Bronsted-Lowry base and water is a Bronsted-Lowry acid are in equilibrium to form hydronium and hydroxide. This is an equilibrium process just like all the other equilibrium process we've talked about, but it's special. Now we can write an equilibrium constant expression for this. And we would set this equilibrium constant expression up just like any other equilibrium constant expression we would set up, but realizing that water on the left-hand side as a reactant is a pure substance. These are just one, and that gives us the equilibrium expression for this process, this autoionization of water, to be that the equilibrium constant is equal to the concentration of hydronium in solution times the concentration of hydroxide solution. And this equilibrium constant expression, the K for this, gets another special designation, Kw, which we refer to as the ion product constant or the equilibrium constant for the autoionization of water. Now at 25 degrees Celsius, we know that this Kw, or this ion product constant for water, is 1.0 times 10 to the minus 14. If you want to be a little more specific, it's 1.02 times 10 to the minus 14. But for now, we'll just consider it 1.0. And this is now a very powerful relationship for us to use. What we know is that in any aqueous solution, we're going to form some hydronium and some hydroxide, and that the product of the concentration of hydronium and the concentration of hydroxide at 25 degrees Celsius is going to be 1 times 10 to the minus 14. So our aqueous solution, the concentration of hydronium and the concentration of hydroxide equal 1 times 10 to the minus 14. So let's work on a couple problems here with that relationship. The first thing we want to understand is in the majority of circumstances, we'll be working with that Kw, that ion product constant at 25 degrees Celsius, which we see up here, 1 times 10 to the minus 14. It's important to note, though, just like any other kinetic processes or equilibrium processes, as we change temperature, we're going to change that equilibrium constant as well. In this case, temperature will affect the ion product constant, that Kw. And you can see as temperature gets colder, that Kw gets to be a smaller value. As temperature goes up, that Kw gets to be a larger value. Now again, unless otherwise stated, it's safe for us to assume that we're dealing with 25 degrees Celsius and the ion product constant Kw 1.0 times 10 to the minus 14. So go ahead and hit pause, take a crack at these problems, and we'll be right back with the solutions. So we know that Kw is equal to 1.0 times 10 to the minus 14, which is equal to the concentration of hydronium times the concentration of hydroxide. Recall, we can shorthand hydronium to H plus. this and that, they mean the same thing. We understand that H plus doesn't exist in aqueous solutions. It's going to form hydronium. But for the sake of simplicity, we often write it as H plus so that it's easier. So now the first problem, calculate the proton concentration in a hydroxide solution that is 0.01 molar or 1 times 10 to the minus 2 molar. So we know the relationship, right? That the proton concentration times the hydroxide concentration equals 1 times 10 to the minus 14. Rearrange this equation so you can solve for the proton concentration. 1.0 times 10 to the minus 14 divided by the concentration of your hydroxide, 1.0 times 10 to the minus 2, you get 1.0 times 10 to the minus 12 molar. Now I suggest at this point double checking to make sure your answer jives. And we see when we plug our concentrations back into our relationship for Kw that 1 times 10 to the minus 12 times 1 times 10 to the minus 2 equals 1 times 10 to the minus 14. We approach the second problem in the same way, right? We know that the Kw is 1 times 10 to the minus 14 is equal to the H plus concentration times the OH minus concentration, which we were given. Rearrange our equation. To solve for the proton concentration, we get, with rounding, 5.6 times 10 to the minus 6. We can then double check this answer by taking the proton concentration times the hydroxide concentration, and that should equal the Kw. And we see it's 1.008, so down to this 4 significant digit because of rounding, but that is equal to our 1.0 times 10 to the minus 14, and we are finished. I'm sorry, did I say we were finished? What I meant to say was, hey, let's do a couple more problems. This time, let's do a little bit more problem solving by solving for the hydroxide concentration. The first one's straightforward, like we saw with the proton concentration before, but then we've got a few other problems to work on. So hit pause and we'll be right back. So for our first problem, we work it just the way we did on the other two. Kw is equal to 1 times 10 to the minus 14 is equal to proton concentration times hydroxide concentration. So we have 1 times 10 to the minus 14 is equal to 2 times 10 to the minus 6 times the hydroxide concentration. We rearrange to solve for the hydroxide concentration, and we get 5 times 10 to the minus 9 molar hydroxide concentration. We can take that, plug it back in to double check. 2 times 10 to the minus 6 times 5 times 10 to the minus 9 equals 1 times 10 to the minus 14. For the second problem, we haven't specified concentrations. We've just said that they're equal, but they're equal at 25 degrees Celsius. They're equal, so we're just going to put them both to x. So we can say that Kw is still 1 times 10 to the minus 14 is equal to the concentration of x times the concentration of x. We can rearrange that to be x squared. Now we can take the square root of both sides. So we've taken the square root of both sides. The square root of 1.0 times 10 to the minus 14 is 1 times 10 to the minus 7. The square root of x squared is x. Therefore, the concentration of hydronium, or a proton, is equal to the concentration of hydroxide. They're both equal to 1 times 10 to the minus 7 molar. This next problem required a little more thought. We know that the proton concentration is equal to 100 times that of the hydroxide concentration. Now we don't know either one, so we just say that the hydroxide concentration is x, therefore the proton concentration is 100x. So now we can plug that into our equation. The Kw, 1 times 10 to the minus 14, is equal to 100x times x. So 1 times 10 to the minus 14 is equal to 100x squared. Divide both sides by 100. Take the square root. You get x is equal to 1 times 10 to the minus 8. Or for the hydroxide concentration, that's 1 times 10 to the minus 8 molar. Now the concentration of your proton or hydronium in solution is 100 times that, which is 1 times 10 to the minus 6 molar. And again, if you take the product of these two, 1 times 10 to the minus 8 times 1 times 10 to the minus 6, you will come back to your Kw, 1 times 10 to the minus 14. So these numbers that we're working with are enough to make people insane. 1.4 times 10 to the minus 6, or 0.0000014, or maybe something like this, 6.5 times 10 to the minus 9. Well, let's hope I get this one right. 0.00000000065. Did I get that right? Oh, forget it. Let's just erase all of it. Why? Because we use a scale that I think most of us are familiar with that make these numbers much easier to handle, and this is the pH scale. pH is defined as the negative base 10 log of the concentration of hydronium. So what we're going to do is we're going to take these numbers with exponents that range from 10 to the minus 2 to the 10 to the minus 14, or even lower sometimes, and we're going to put them on a scale that's easier for us to grasp, and that's the pH scale. So let's just take a look at how pH can make our life a little bit easier. Blood, right? Your blood has a small range of proton concentration, but we'll just say that your hydronium concentration in your blood is about 4.2 times 10 to the minus 8 molar. Go to something more acidic, the stomach acid in your belly. The proton concentration is about 7.9 times 10 to the minus 3 molar. These are big ranges in numbers if we were to write them out, and they're often cumbersome to handle. But if we take the negative log of these and put these on the pH scale, let's look at how it makes these numbers easier to handle. So when we take the negative log of these hydronium concentrations, we can see for blood, the negative log of 4.2 times 10 to the minus 8, we get a pH of 7.38. Much easier number to handle. When we take the negative log of the hydronium concentration in your stomach acid, 7.9 times 10 to the minus 3, right, we get 2.10. Again, much easier to handle. Now, when we're dealing with our answers after the log function operation has been done, you notice that my significant figures don't match up here and here. That's because with the logarithm, the first number is representing the order of magnitude that we deal with. So we took a negative log. So it's really representing that 10 to the minus 8 there. It's these second two numbers here that represent our significant figures from our original measured value. So if we want to talk about the pH of pure water at 25 degrees Celsius, we know, again, our ion product constant here, Kw, is equal to 1 times 10 to the minus 14. In pure water, these concentrations are equal, and they're both equal to 1 times 10 to the minus 7. So in pure water, the pH is going to be the negative log of 1 times 10 to the minus 7, or a pH of 7, and that's what we think of as neutral. So a solution that's acidic, or an acid in water, is going to have a higher hydronium concentration than pure water, and its pH is going to be less than 7. And we see that right here. An acidic solution has a greater concentration than 1 times 10 to the minus 7, and its negative log or pH value is going to be less than 7. For something that's basic, it is going to have a lower hydronium concentration, or you could think of it as a higher hydroxide concentration, and its pH will end up being greater than 7. So neutral solution, our hydronium concentration is equal to our hydroxide concentration, and our pH is equal to 7. In an acidic solution, our hydronium concentration is greater than 1 times 10 to the minus 7, and our pH is less than 7. In a basic solution, our hydronium concentration is less than 1 times 10 to the minus 7, and our pH is greater than 7. Here's a table of some common substances and their pH ranges, but I think what this table really illustrates for us is if we take a look at our hydronium concentration and our pH on this side of the table, we can take a look at pure water here, neutral, 1 times 10 to the minus 7 hydronium concentration correlates to a pH of 7. Notice the exponent and the pH. As we get more acidic, we get more concentrated hydronium concentration, 1 times 10 to the minus 6, pH of 6, 1 times 10 to the minus 5, pH of 5, 1 times 10 to the minus 4, pH of 4. You get the picture there. And as we get more basic, 1 times 10 to the minus 9, or less hydronium, pH of 9, 1 times 10 to the minus 11, pH of 11, 1 times 10 to the minus 14, pH of 14. So you can see the relationship between the hydronium concentration and the pH scale. What's useful is we can take the negative base 10 logarithm of any set of numbers and put them on a p-scale, right? Simply by taking the negative log of the hydroxide concentration, we can create a pOH scale, or we can take the negative log of equilibrium constant values. For instance, pKa is simply the negative log of the Ka value. And that allows us to look at the pKa values. As the pKa value goes down, gets closer to 1, those protons are more acidic, or those acids are more likely to dissociate. As the pKa value gets larger, that is indicating that those molecules are less acidic. So we can tie this together with the relationships we've been discussing. We know that in water at 25 degrees Celsius, the concentration of hydronium times the concentration of hydroxide equals Kw, or 1 times 10 to the minus 14. Well, mathematically, we could take the negative logs of both sides of this equation. So we can take the negative log of the hydronium concentration plus the negative log of the hydroxide concentration, and that equals the negative log of Kw, or the negative log of 1 times 10 to the minus 14, which is 14. Or in other words, the pH that comes from this plus the pOH, which comes from this, equals pKw, or equals 14. pH plus pOH equals 14. So let's tie these concepts together with a few practice problems. Why don't you go ahead and get started on these, hit pause, and we'll be right back with some solutions. So first, we can find the pH by taking the negative log of the proton concentration, which was given. From there, we know the relationship between pH and pOH. They equal 14. Therefore, for part A, the pOH is 12, the pH is 2. Given the hydroxide concentration, we can find the pOH, the negative log of the hydroxide concentration. The pOH is equal to 8.74. We can then find the pH. 14 minus the pOH equals a pH of 5.26. Lemon juice, proton concentration of 3.8 times 10 to the minus 4. We can use that to find the pH, take the negative log. We get a pH of 3.42. Calculate the pOH, 14 minus 3.42, pOH of 10.58. And from your ammonia-based window cleaning solution, the hydroxide concentration is 1 times 10 to the minus 6. We can calculate the pOH by taking the negative log of the hydroxide concentration, get a pOH of 5.27. pH is equal to 14 minus the pOH. pH is equal to 8.22. Let's just take a closer look at this figure here and what it's showing us. So as our hydronium concentration increases, right, our pH goes down. But notice how as our hydronium concentration increases, our hydroxide concentration decreases. Or as our hydroxide concentration increases, our hydronium concentration decreases. And the relationship between pH and pOH, right? pH plus pOH equals 14. As pH goes down, pOH goes up. As pOH goes down, pH goes up, right? So they're working together. It's just, are we looking at the hydronium concentration or the hydroxide concentration. So here's a couple of problems more for you to practice on. Go ahead and get started on these, and I will be right back with the solutions. So if we're given the pH, we know that the pH is the negative log of the hydronium concentration. So we can take the inverse of the negative log, or 10 to the raised to the minus pH value to get our hydronium concentration. So here the hydronium concentration is 1.7 times 10 to the minus 4 molar, or more concentrated what a solution of pH 7 would be, which would be 1.0 times 10 to the minus 7. So lower pH, higher concentration of hydronium. On the next problem, we have a higher pH, a more basic solution, pH larger than 7, but we follow the same process, take the inverse of the negative log to get the hydronium concentration, 6.6 times 10 to the minus 10 molar, and that is a smaller concentration that we get at neutral pH of 1.7 times 10 to the minus 7 molar. All right, now all the practice problems we've done in this section and the lecture before are going to be very useful when we get to our next section, where we take all of these relationships and apply them to solving equilibrium problems.